Hello everyone. I'm going to talk about the experiments and modeling of wet curing on the curling of cement paste from drying shrinkage, which was published in two papers that I'm going to talk about today. The work was done by Hajibabaee, Tyler Lay, and Zachary Grasley from Oklahoma State University and Texas A&M University. The work was published in two papers, as you can see, in the ACI Material Journal and the Cement and Concrete Research, and it was funded by Oklahoma Department of Transportation and Oklahoma Transportation Center. So first I'm going to talk about the impact of wet and seal curing on curling in cement paste beams from drying shrinkage, which was published in the ACI Material Journal and was written by Hajibabaee and Tyler Lay of Oklahoma State University. First, I'm going to talk about the backgrounds, methodology, results, and discussion, and the conclusion. So when cement particles react with water, a slurry generates around the particles. After a few hours, which is probably 4 to 6 hours, it hardens and the slurry transforms into a viscoelastic solid. And because of the internal chemical reaction and because of the external moisture loss, we will have some water removal from the system. The volume change that is actually caused by the water removal from the system and the pores is usually called drying shrinkage. And the drying shrinkage is happening right after the system is exposed to a relative humidity, which is below the equilibrium value of the pore solution. After that happens, the water evaporates from the system, as you can see here, and that causes some generation of the meniscus and therefore some capillary suction near the exposed surface of the system. So drying can happen from either side of the element. For example, when it happens from these two sides, we will have a constant shrinkage over the entire depth of the sample, which can cause some kind of an axial length change, or if it's restrained, it can also cause some cracking. But when it's free and there's no restrainment, such as what we have in the concrete pavement or the slabs, and when the drying happens from only one side of the sample, we will have more shrinkage on the exposed surface and less shrinkage at the bottom. This differential shrinkage can cause some deflection, which is called curling or warping, which I'm going to call curling from now on. And because of these curled edges, when traffic goes on top of it, for example in the highway, we will have some unwanted serviceability issues like cracking. How does wet curing impact curling? As you know, the purpose of curing is to maintain moisture and temperature in the concrete that can help develop a tighter microstructure. Therefore, curing can increase the durability and strength and water tightness and abrasion resistance. But there are some challenges. Prolonged wet curing is thought by many people that can provide only improvements, such as what I've shown in the previous slide. For example, the current Darwin amine sulfur, which is a widely known sulfur in the United States for pavements, it says that there is a 300% reduction in the curling after using the prolonged wet curing. But there are varied opinions in the literature about the impact of wet curing and the prolonged wet curing. For example, there are people like Prencio, Hedenblad, and Hajibabaee and Lay that showed that when we increase the wet curing, we will have more drying shrinkage, or in other words, shorter curing can cause less shrinkage gradient. But other researchers said that there is only a delay in the drying shrinkage and little effect on the magnitude of the curling. So today I'm going to talk about the experiments that we have done at Oklahoma State University, which were showing the impact of increased wet curing. We used this type of very thin, long paste beams, which were coated on all sides except the exposed side, which was under the different lengths of wet curing, seal curing, and no curing. And the test was modeled after work by Berg et al. In 2004. We used different water to cement ratios, and we used different lengths of wet and seal curing. 0, 1, 3, 7 and 14 days of wet curing, and 1 and 3 days of seal curing. So after we remove the wet curing, or terminate the wet curing, and we remove the wet burlap, as you can see, the sample is losing water from the top. All sides are sealed, so it starts curling up. So this moisture loss from the system is shown in this graph versus the days exposed to drying. This is the no-cured sample. As you increase the duration of the wet curing, there is less mass loss in the system, which is statistically different. 3 days, 7 days, and this is the 14 days of wet curing. So there is less mass loss in the samples that had the maximum wet curing duration. So additional curing will sustain hydration and decrease the porosity and permeability of the cement paste. And this decrease in permeability makes it more difficult for a specimen to lose moisture from drying. And this is why the specimens that were cured longer lost moisture at slower rates. So the deflection that I showed in the previous slides was measured through this caliper at the middle of the sample because the deflected shape was very symmetric, so we were able to measure the maximum curling from the middle of the sample. As the sample was drying after termination of curing, the curling was increased. This is after 3 days, and then it starts curling back down up to here, which was day 12 from the exposure. So if I just show the maximum curling versus the days that I measured those curling on a graph like this, you can see for wet curing, it's like a curling up to a maximum after about 4 days, and then it curls down. As you increase the wet curing, the magnitude of the maximum curling and also the time to reach the peak of deflection is increasing. This was very unconventional in the beginning, so we repeated this test several times, and we also used different water to cement ratios, and we got the same results each time. This is for 14 days, which had the maximum amount of curling. So additional curing can sustain the hydration, and that decreases the porosity of the system. Because of the reduction in the pore radius, you will have a higher capillary pressure according to this equation. And because of the refinement in the pore structure and the water gain from the wet curing, we have a higher degree of saturation, which I'm going to talk more about in the next paper. And because of that, we have a higher shrinkage in the paste. Also, if I just show the 1 day wet and 3 day wet curing from the previous slides, this is the mass loss, this is the maximum curling versus the days that I measured them, versus the seal curing for 1 day and 3 day. You can see that there is a similar trend. As you seal cure longer, you will have less mass loss. This is the same trend in the wet curing, with a little bit difference because we didn't have any mass gain from seal curing. The samples were only sealed inside the bag for 1 day and 3 days, and then they were exposed to dry. And this is the maximum curling height, and you can see their differences are very small. Basically there is no statistical difference between the 1 day and 1 day wet curing and 1 day seal curing, and there is no statistical difference between the 3 day wet curing and 3 day seal curing. And as you increase the curing length, you increase the maximum curling. Also, the time that the maximum deflection happened in the seal curing was shorter, and this can be related to the more water gain to the wet curing samples. So the maximum curling is similar between the wet and seal cured samples cured for comparable durations, and this suggests that the capillary pore size range and hence the shrinkage of the hydration products on drying were very similar between the samples despite the additional water used in the wet curing for the duration investigated. And also it is likely that the water which was gained through the wet curing was only feed the larger pores, so there wasn't that much of an impact from the wet curing in the wet cured samples. For comparison between different water to semen ratios, as you remember, this was from the 0.42 water to semen ratio, which I talked about first, and the trends were explained. The maximum curling happened in the samples that had the longest curing, and they also had the least amount of mass loss. But when you decrease the water to semen ratio, as you can see in this graph, the trends were very similar, but there was less curling and less mass loss in the samples with the 0.34 water to semen ratio. So, as you can see, the samples that had no curing for both water to semen ratios had a very similar maximum amount of curling, although their mass loss was very different. So samples with the water semen ratio of 0.34 had a lower maximum curling and a lower drying rate than samples with the water semen ratio which was higher, about 0.42. And there was little difference in the maximum curling for samples that had no additional curing, despite having a significant difference in the rate and amount of moisture loss. And more research needs to be done to understand this phenomenon. But what are the mechanisms? So in the next paper, I'm going to talk about the mechanisms of dimensional instability caused by differential drying in wet cured cement paste, which was published in Cement and Concrete Research. The paper was done by Amir Hajibabaee, Tyler Lay, and Zachary Grasley from OSU and Texas A&M. There were three mechanisms that we talked about in that paper. One was the capillary forces. So when drying happens, the water begins to empty and it starts from the larger pores, and then the radius of the pores becomes smaller while this drying is happening, and then the smaller pores begin to empty, as you can see in this graph here. So because of the reduction in the pore sizes, there is a differential pressure around the exposed surface which was drying. So if this is a picture from the samples that we showed in the previous paper, the maximum amount of pressure is happening near the exposed surface, which was in a lower relative humidity than equilibrium relative humidity of the pore solution compared to the bottom of the sample, which was still and around 100% relative humidity. And this capillary force is the prominent mechanism when the pores are larger than 10 nanometer. But when they start to refine and becomes smaller, there is another mechanism that can contribute this to this drying shrinkage, and that is the disjoining force. And both of these disjoining force and the capillary forces, as you can see here, they can be called as the capillary pressure in the literature, which is shown according to the Kelvin-Laplace equation, and that's related to these two parameters, which were the radius of the pore structure and the disjoining pressure. And once the drying happens, the relative humidity in the system is decreasing, and on this side of the equation also we have a increase in the capillary pressure. So these two forces are basically describing the forces only in the saturated portion of the body. But in reality, we have a partially saturated system. And there is another mechanism that can play a role, and that's called the surface energy of the system. The degree of saturation, which is basically the ratio of the water filled pores to the total porosity, is shown here. And it was taken into account the very first time by Daleband's team in 1998. They used the partially saturated porous Vickers glass, as you can see in this picture, and they used degree of saturation to define the shrinkage in the material, and they showed that not only the capillary pressure are important, but also the degree of saturation. So Kusi in 2004 formalized the use of degree of saturation and combine all of these mechanisms and define the effective pore pressure, which is according to this equation, and is related to the degree of saturation and the capillary pressure. So to better understand the mechanism behind this phenomenon, we designed another test to understand more about the degree of saturation. So we made these very tiny paste cylinders, which were about half-inch thick and half-inch diameter. And after using different duration of wet curing under top, we demolded them, we sectioned them from the top, middle, and the bottom, and we put them in containers with 4 different storage relative humidities, which were monitored using the salt solution, 4 different salt solutions. The more details are found in the paper. We used the same amount of wet curing, and the samples were monitored for their mass change for about 2 weeks, and then the mass change was negligible, and we put them in the oven, and also we submerged them and saturated them to find these degree of saturation graphs. So if this is the depth of the sample, which is half-inch, or basically the same as the thickness of our paste beams, which I've shown in the previous paper. For example, for the highest humidity that I used to monitor the section cylinders, as you increase the wet curing duration, the degree of saturation is also increased at all depths, and also there's a statistical difference between the top and the bottom degree of saturation in the samples. When you decrease the relative humidity, the degree of saturation is also decreased. So now that we have the degree of saturation, we can use an analytical solution for a one-dimensional approximate linear drying diffusion problem, which was formulated by Grasley, and we can use the results from the mass loss of the cement paste beams and the cylinders that I talked just recently. And we can use them as the input parameters in the model, and we can calculate the free strain and deflection of the samples. So I used this equation, which was a refined version of what I've shown before, using the concentration of the dissolved species, and we used this equation that I've shown before, which was the additional pressure by free energy of the surface, and we used the combined as the effective pore pressure, and we defined this free shrinkage of the sample, which was basically using a lot of mechanical properties, as you can see here. And I just want to highlight the impact of the rate of effective pore pressure, which I'm going to talk about later. And then we use those strain that we found, and through the use of the Euler-Bernoulli equation, we were able to find the maximum deflection of the samples. So first I'm going to compare the experiments versus the approximate linearized model. And I use these mechanical properties like pore volume fraction, the bulk modulus of the solid phase, and the Poisson ratio, and these other parameters the same for all of my curing methods. And that was because I was just wondering if the model is showing exactly the same results and trend basically as the experiment. So this is the model results for the experiment, which is in blue line, versus the model which was in the solid line without error bars. And as you increase the duration of wet curing, we notice that the trends are the same. So both the model and the experiment are showing that there is a increase in the magnitude of the deflection by increasing the wet curing, and also the time to reach the peak of deflection was also increasing. So you can see that the maximum deflection happened for the 14-day wet curing for both model and the experiment. So if I show only the peak deflection, which are basically here in one graph for both the simulated results and the measured results, there is not that much a statistical difference between the two. So the model was in a very good agreement with the experiment. Also, because of the request of the reviewer to use a nonlinear solution next to our approximate linearized model, which I showed before, we used this equation, which was basically showing that the drying diffusion is changing over the depth with the change in the relative humidity over the depth. And we found that experiment nonlinear in the red and the approximate solution in the green, they basically show the same trend. And as you increase the duration of the wet curing, the magnitudes and the time to reach the peak of deflection is also increasing for all of them. So in general, both the approximate linearized solution and the nonlinear solution, they showed that the deflection gradually increases and reaches a peak of deflection and then decreases as drying continues. And the models also show that with increased wet curing, the peak is also delayed and increases in magnitude. And the overall deflection prediction by the linearized solution are comparable to the results from the full nonlinear solution. This indicates that drying diffusion may be linear for the tested samples. So this graph shows the effective pore pressure, which was basically the combination of all driving forces that we talked about in the paper for the finished surface versus the sealed surface for some given drying times like 1, 3, 7, 15, and 30 days after exposure. And it shows that basically the effective pore pressure was the maximum around the finished surface, and as you increase the duration of the wet curing, the amount of the effective pore pressure is also increasing. And this green dashed line shows the rate of effective pore pressure, which I talked about in the strain equation, and it basically shows that the rate or the gradient is also increasing as you increase the duration of wet curing. So in summary, the effective pore pressure for the samples that are cured longer, which have a refined pore structure, as you can see here, versus the uncured pore network, they have a higher degree of saturation, and because of that, the effective pore pressure is higher for the samples that are cured longer, and this magnitude is larger near the exposed surface, which is lower relative humidity compared to the bottom of the sample, which was sealed and had a higher relative humidity. So what does this mean? So as we all know, wet curing can increase the strength, stiffness, and the resistance to surface abrasion, and we showed here that it also reduces the mass transport, increases the degree of saturation, and increases the capillary forces near the surface on drying. And because of these, it takes longer for the concrete to dry, and once it dries, we will have a greater surface shrinkage. And because of the greater surface shrinkage, we can expect a higher amount of gradient over the depth, which can cause larger curling. So wet curing slabs will cause increased deflections from differential drying, and this phenomenon is more severe in lower humidities, such as 40% that we use in this experiment. And if, for example, one wants to wet cure slabs for other reasons, then they can add reinforcing steel, increase thickness, or reduce paste content of mixture. And also, I'm going to talk and summarize about what I found in severe drying conditions like 40% relative humidity. Wet curing can increase the potential for surface drying shrinkage and curling of slabs on grade or pavement. And due to wet curing process, we have a refinement in the pore structure, which can reduce the permeability and porosity, and this reduction in the pore sizes can cause a higher degree of saturation after curing longer, and also it produces smaller pore sizes, which in turn suggests greater capillary tension and induce a strain upon drying. So the study showed that both through the experiment and the mechanistic one-dimensional drying shrinkage model that was developed by Grasley's team, that prolonged wet curing can cause an increasing of the magnitude of the shrinkage strength gradients and therefore curling. And all of these can be easily done by measuring the desorption isotherm as the input parameters in the model. But it should be pointed out that there are other important benefits for some other important concrete properties from wet curing, such as the strength, permeability, abrasion resistance, and also care should be taken to apply these findings for the samples that have a different boundary condition from the samples that we used in this study, such as, for example, different boundary conditions, support, restraint, and temperature. In the future publications that we are working on right now, I'm going to talk about the impact of higher ambient relative humidity and not just the severe drying condition on the drying shrinkage induced curling, and also the impact of different curing methods on beams that were in the field condition and on a full-scale pavement in Oklahoma. The papers were published in the ACI Material Journal, as you can see here, and the Cement and Concrete Research. Thank you.